Yeah, thank you very much. So yeah, let me start. So today I'm gonna talk about homological mirror symmetry for hypersurface singularity, and yeah, I'm planning to give several talks about this topic. So today I just want to introduce the basic theory of this mirror symmetry for singularity. Okay, let me start. So let me introduce so-called invertible polynomials. So let f be some polynomial x1 to xn. I consider this is a weighted homogeneous polynomial. So this means that this is weighted homogeneous polynomial. This means that there exists weight w1 to wn and d some natural numbers such that this w lambda 1 x1 lambda wn xn is equal to lambda to the d f x1 to xn. So I consider this weighted homogeneous polynomial, which means that I have this w1 to wn and d such that this satisfies this condition for every lambda in system. Okay, and I will call this w1 to wn and d to be the system of weights. Yeah, and then I have this definition: a weighted homogeneous polynomial f x1 to xn is invertible. I don't know why. It's invertible if it satisfies the following two conditions. First, f can be written in this way: fx1 xn can be written as this n, sum of n monomials. So with some constant xi, xj, e, ij. So f can be written as a sum of n monomials, and such that for ci is non-zero and ei0 is non-negative element in the matrix for I, j from 1 to n. So there is n by n matrix whose entries are non-negative, and so there is some constant ci. So I should be able to write f in this way. And sometimes it doesn't, without loss of generality, I can assume this to be 1 sometimes. So it doesn't change the topology of this polynomial. So I just sometimes assume ci is 1. And second, this E, this matrix E ij is invertible. If my polynomial satisfies these two conditions, then I will call this polynomial to be invertible. And so the definition is that an invertible polynomial is non-degenerate if it has an isolated singularity at 0. So if my polynomial satisfies this condition, then yeah, I will say this is non-degenerate. So in this case, so yeah, and from this condition, this weight condition, so I can, so I mean, let me say this way. From this weight condition, there exists unique solution of the equation. So E times this is this matrix times this W1, this Wn is determinant of E times 1, 1, 1. So I mean from this weight condition, so if I consider this equation, there's always a unique solution of this equation, and let D be a determinant of E, and so I mean I can always find I mean whenever I have this how can I say, invertible polynomial, I can always find this weights W1 to Wn and D, and I will say this W1 to Wn and D be the canonical system of weight, and yeah, I will, yeah, this is another notation, so this is some GCD of this number, and when this is 1, then I will call this system is reduced, and when this GCD is greater than 1, and I will call this system is non-reduced. Yeah, this is just terminology, but yeah, let me introduce this notation. Is there any question? Okay, so yeah, if there's no question, so anyway, yeah, this is very important property, definition, so please, yeah, remember this one. So and then, so indeed there is classification for these invertible polynomials. So there is a theorem by Kruger and Skake. So the theorem is that any invertible polynomial is a Tom-Sebastiani sum of chain type polynomial and loop polynomial. So I mean, yeah, I will explain these two terminology, but for any invertible polynomial, I can always make some base change, coordinate change, and then I can write it as a Tom-Sebastian sum of these two types. So first chain type is nothing but a polynomial looks like this one: x1, a1 plus x1, x2, a2 plus x m minus 1, m minus 2, x m minus 1 to the a m minus 1 plus x m minus 1 x n to the a n. So where in this case a1 is greater than equal to 2 and a n is greater than equal to 2. So this is so-called chain type, and loop type. A so-called loop type. Loop type is something similar, but there's more modification. So x1 to the a1, x2 plus x2 a2, x3 plus xn minus 1 a to the an minus 1, xn plus xn an x1, where n is greater than or equal to 2. So I can always, so these two types are basic types of this invertible polynomial. And please note that when n is 1, then this chain type is nothing but, when n is 1, then these terms are all 0. So then I obtain x1 to the a1. So sometimes people call it Fermat type. Right? So this is called Fermat. So I mean, when n is 1, then I obtain this one, and by Tom Sebastiani, I can obtain x1 to the a1 plus x2 to the a2 plus blah blah blah. Okay, so anyway, these this chain type and the loop type, sometimes Fermat type, are basic building block of this invertible polynomial. Is there any question?
So the condition for the equality is for the chain type we have the a1 and n is
A1 is greater than or equal to 2. Yeah. So n do not have to be equal to 1. So I mean, for this case, n is greater than or equal to 2. But for this type, I don't assume that this n can be 1. Then this gives me just this term. Yeah. Thank you very much. Thank you for the question. So any other question? Okay, if not, let's go further. So for this case, you can, check that. Okay, so for this chain type, you can check that this, for this type, okay, so chain type case, you can compute this matrix. Chain type case, this matrix E is, so when, how can I say, n is 1, this is A1. Okay, this is, polynomial of having n, adding sum of n monomials, right? And so this term, it's A1. 1. Pardon? Okay, if there's, okay. And this time, this is 1A2. Right? So this is, this is x1, E1, 2, E. So this is x1, E21, x2, E22, right? So, sorry, it's here. And this x2, x2 times x3, a2. So this is x2, a3, 2, and x3, e3, 3. So this is 1a3, and select this one, right? So, and the final term is, 1 times a1. And so for this chain type case, the matrix is of this form. And the loop type case, you can also compute this one. Loop type case, it's a1, 1, a2, 1, like this, an, and there's x1, so I have 1 here. yeah, so 1, 1, and this one. Okay, and yeah, then you can check that these are invertible polynomials. Okay, so then go further. Then we can introduce so-called Berglund-Hubsch transpose. So yeah.
How you assuming all of the AI is non-zero?
Yeah, right. So all AIs are non-zero. Yeah, because this must be invertible.
Especially A1 and AN for the chain type is greater than.
Yeah. So I mean these there are conditions, but for other cases it's a non-negative integer. Yeah. And yeah, because this has to be invertible, so this must be greater than equal to. Thank you. So yeah, and I forgot that. I forgot to mention one important thing. So I mean, yeah. So this is a kind of a survey talk. So yeah, I mean, most of things. Most of explanation I borrowed it from paper of Takashi, and Evelyn. So there's survey paper of these two authors. So I mean, yeah. So survey paper and article talk by Takashi, and also survey paper by Evelyn. I will borrow many explanation from there. Okay, and anyway, let me explain this Berglund-Hubsch transpose. Let me explain what it is. So let F be this invertible polynomial. Invertible polynomials. Then I don't know why this. Sorry, just 1 minute. Okay, let me. Let's start from. I will start from this invertible polynomial. Then f tilde, I define a new polynomial this way: Cn and Ci and this j from 1 to n and x e j i. So I mean, I just take transpose over this matrix. So this is x to the e j i, and the same other things are the same. So I will call this polynomial to be Berglund-Hubsch transpose over F. Yeah, then I mean, later you will see that this polynomial and this polynomial are kind of mirror to each other. But in order to say that, I need to introduce some symmetry acting on this polynomial and this polynomial. So let me define several symmetry groups acting on these two polynomials. So let GF to be some group, looks like this one. So C star n, this is a subgroup of C star to the n, such that this f lambda 1 x1 lambda n xn is nothing but f x1 xn. So I define a group here, and you can easily see that then this group acts on this, this f. And I can define another group group LF. So which is I define this way. So 1 to n and z. So this is xi plus z f. These are, I mean, generator of free. I mean, I consider free abelian group generated by this symbol and this symbol. So this, how can I say, xi and f are, how can I say, symbol, and I consider this formal group, free abelian group generated by this generator, and I model out this group by this relation. Ij xj from j1 to n, where I is from 1 to n. So I model out this free abelian group by this relation. Okay, then I will consider again this gf hat, and this is nothing but spec of this cf. Okay, and I can check that I can write this group in this way. So lambda 1, lambda n, star n. That this product of j from 1 to n, lambda j, eij is equal to j from 1 to n, lambda j, eij. Sorry, enj. This is 1. Yeah, so I can define this gf and gf hat, and yeah, there's so one more definition. So this is due to Berglund and yeah, Penninson. So yeah, different group. So I mean Berglund, yeah, he contributed this one and this one, but yeah, this time Hellingsen, Berglund and Hellingsen defined for a subgroup G in GF. Then we can define its dual group. Its dual group G tilde is defined this home. So this is subgroup. So I mod out this abelian group by this G, and I consider its dual. And this G hat is defined in this way. Is there any question? Okay, if not, let me. Yeah. So. Yeah. Then, as you see, I mean, how can I say, for this chain type, I have this matrix. So then I can easily compute this Berglund-Hubsch transpose of F by this matrix. And again, for loop type, I also have this matrix, so I can also compute this F dual. Okay, so from F, I obtain this F dual. And for any, and I again define this GF. And for any subgroup G of this GF, I can define its dual group G tilde. So yeah. So then, there's a surprising conjecture. Yeah, let me use this blue pen. So there's a surprising conjecture by this Berglund and Hubsch and yeah, Hellingsen. Sometimes people call it just the Berglund-Hubsch, yeah, conjecture. But anyway, so they conjecture that this Fg is mirror to this F tilde and G tilde. So this is their conjecture. So I mean, yeah, I define all these terms. So f, when f, so if this is invertible polynomial, then f tilde is just Berglund-Hubsch transpose of f. And for any g, which is subgroup of this gf, then this g tilde is nothing but hom gf cos g system. In any case, then, I mean, they claim that, so by some physical argument, so from some physics argument, they claim that, okay, this must be mirror to this one. So for the simplest case, I mean, so let's consider this f. G is gf itself. So this example. So when G is gf itself, then its mirror is nothing but f tilde is the same. But because G is gf, this is trivial group. So I just consider this trivial. Yeah, this is simple case, but I mean, so how can I say? How can I, in order to say mirror symmetry, I should say some kind of A model and B model and some A model here and some B model here. And sometimes, for example, when G is non-trivial, it's quite delicate problem how to define. So this A model for arbitrary F tilde and G tilde. So I mean, sometimes people just consider, yeah, this to be trivial, and then consider this case. Okay, so that's the conjecture. And yeah, is there any question? I see. So yeah, is this blue pen is this a blue pen is okay? Okay to see? Is it visible? I see.
Yes.
Okay, thank you. Let me go further. So then let me, how can I say, show some topological evidence why people think, maybe not topological, but theoretic evidence why these two, it is natural to think these two pairs to be mirror. So that's the, let me explain a little bit about this one. So for the using this Obifold E function. Okay, so let me briefly recall setting. So I start from this invertible polynomial f. Then I consider this polynomial as a map from C to C, and I assume that this is non-degenerate and invertible. So please recall that this non-degenerate means that this polynomial has an isolated singularity at the origin. And then, as usual, we consider this Miller fiber. So I consider some small ball around the origin, and I also consider some target. So this is what we have done many times during this seminar series. So I mean, I consider some small ball T here, and I consider small ball T, and I consider its inverse image. So it's inverse image, and for general fiber it's smooth, but this singular fiber origin. Okay, and I consider small neighborhood X, which then. So, and let's take this map to here. Yeah, anyway, this is what we have done many times. So I consider this f from x to t, where I have this 1. Okay, and then by so far, I mean, by Stingbrink, as we discussed many times, there exists a mixed Hodge structure. Hodge structure on, yeah, let me, here. There exists a mixed Hodge structure on, in this case, H n minus 1. So previous time I consider C as a map from Cn plus 1 to the C, but I mean this is just a small change of notation on this vanishing cohomology anyway. And I have this monodromy, and I can decompose this by semi-simple part and idempotent part. And similarly, what we have done, we consider this this eigenvector space, which is kernel of this Ts minus lambda, where this is map from -1 x c. So yeah. Okay, I consider this I denote this H n plus 1 x infinity c lambda to be the eigenspace of this semi-simple part of this monodromy. Yeah, then definition. So let HF be a vector space. Looks like this way. So I consider, like Hodge decomposition, for this singularity case, I can obtain some decomposition of vector space, like what we have done for smooth projective variety. So, and anyway, for this case, this is parameterized by this rational number. But in any case, so I will define this decomposition. So it's defined as, so first, this if P plus Q is not 0, then I define this HF PQ to be 0. Yeah, so if the sum is not n, then I will define this to be 0. And if this P plus Q is n, and when P is integer, then I will define this HF PQ to be the graded pieces of this mixed Hodge structure and of this H minus 1 x infinity c. And this eigenspace 1, eigenvalue 1. And when P plus Q is n, but P is not integer, then I define this HF PQ to be this again graded pieces of this filtration, and this H n minus 1 x infinity c. But in this case, because in this case P is integer and the eigenvalue is 1, for this case this is just 2 pi I e to the 2 pi I p. Yeah. Sorry, this is 2 pi I p. Yeah, so I define new vector space, HF PQ in this way. So then I want to define some Hodge structure or some vector space associated to this pair of function and group. So I will consider this as an OB4. So I will consider some kind of OB4 associated to this F and G. And I want to define some kind of Hutch structure associated to this orbifold. So, yeah, let me give you the definition. Yeah.
The original definition is using the two parameters p, q, but in fact it is just parameterized by only p. Because q is automatically defined.
Yeah. Q is already defined by using. Yeah.
Otherwise, it's zero.
Right. Yeah. Yeah, but definition is exactly. I mean, this Q is exactly the spectrum.
So, for
This
example,
case.
is it a description of more general notion of the Hodge decomposition with the rational?
Yeah, I mean, but how can I say? So far, I just defined this vector space in this way. So I didn't do any. How can I say? I mean, I think there must be some kind of. Sorry. I mean, so far I just defined the vector space in this way, and just add consider direct sum. But I think there must be some more delicate structure. But I mean, to be honest. Yeah. Sorry. No. I
Even it's for me, it's first time to see such a kind of rational parameters for the PQ.
Yeah. But I mean, for this singularity case, I think this rational parameter, I mean, is quite natural, and the spectrum is kind of parameterizing this some kind of parameter over this rational parameterization. Yeah, and so anyway, there is no group action so far, but now I want to encode this group action. So let me define. I mean, let's consider some subgroup G inside this GF, and let me consider an element G, small g in large G. And then, I mean, I consider this fixed G, which is nothing but the fixed point, some fixed point on this G action. So I consider this fixed locus. And NG is nothing but the dimension of this fixed G, and FG is restriction of F to fixed G. And you can check that if I restrict this function to this fixed locus, it still has isolated singularity. You can check this. So I mean, all these, how can I say, discussion can also be applied this FG. Okay, then, I mean, yeah, so then I can again consider this HFG. So I mean, HF is defined here, and I can do the same thing for FG, and FG is defined here. And the fact is that this admits the G action. This is a fact that this admits G action. So then I will define somewhat complicated function fg0. So this is nothing but g to g and h. So for any element here, I can define this vector space in this way. And because this admits a G action, I have this G invariant part. And okay, here this 0 corresponds to this dimension is even. Okay, and I have so-called H. G and H. So it's just a Tate twist, kind of Tate twist here. So I can define some number, and so in some way, and then this is just twist by this minus h and minus h. And similarly, I can define odd degree part. So this is even degree part, and this is odd degree part, and it's same. G equals G, and NG is 1, mod 2, and other things are the same. So I can define this even part and odd part of this obifold, yeah, for this obifold. And then I can define so-called E polynomial or E function. So the E function for the pair fg is nothing but E fg and T bar, and this is nothing but I just defined this way. So this is I consider all pair of rational numbers, and I consider this dimensions of this f h g 0 0 and pq part minus dimension of h f g 1 and pq part, and I consider t p to the t to the p minus n over 2, t bar to the q minus n over 2. Yeah, I mean I consider this E function on this obifold. So I mean, so I define so-called E polynomial for this case, and then yeah. Is there any question so far? And then let me say it this way. So let me give it definition. So when f is non-degenerated invertible polynomial, and when G is subgroup of this GF, and I need some more assumptions. So suppose that, assume that okay, G is, for example, subgroup of this SL and C. So let's assume that this G is subgroup of this special linear group, or I mean, there's a I don't want to explain this today, but I mean there's maybe we can define this for this case, but let me skip this one. And anyway, then I can define the Hutch number of this Hutch number for the pair fg is nothing but h to the pq, and fg, this is nothing but just the dimension of this h fg 0 pq plus this dimension h fg 1 pq, when this p and q are. Yeah. Then now we can describe why now I can explain why this is important for, I mean why it is natural to say the mirror expected by Berglund-Hubsch and Nielsen. Yeah. Let me give you a theorem, state a theorem by Ebeling and Kusan-Jade and Takahashi. So they prove that when f is non-degenerate invertible polynomial, and when G is subset of GF, then they prove that this E polynomial defined via this procedure, Fg and T bar, this is nothing but -1 to the n, and E this F tilde and G tilde, and the T inverse T bar. So yeah, they prove this theorem for any non-degenerate invertible polynomial. This E polynomial of Fg is same as this E polynomial F tilde and G tilde with a certain change of variable. And as a corollary, I think this is this corollary is becoming much clear why this is mirror. So the corollary is that same condition. Okay, so F is again non-degenerate and invertible, and G is not only subgroup of GF but also subgroup of SL and C. Then corollary of this result is telling me that HPQ of Fg is nothing but n minus P Q F tilde and G tilde for every PQ. So as you see, I mean, as you know, yeah, the original mirror symmetry comes from this symmetry of Hutch diamond, and by defining Hutch diamond, the Hutch number of this Landau-Ginzburg model, or I mean this obifold in this way, one can check that this Hutch number also satisfy this mirror. I mean this satisfy this symmetry. Yeah. And this somewhat also gives me some extension of the spectrum we discussed so far. So I mean, so an exponent. So exponent is kind of it's another terminology another terminology for spectrum. An exponent of this Landau-Ginzburg model is a rational number Q such that this HPQ Fg is natural. So I mean, in this way I can extend the classical notion of spectrum for this obifold case, and this set of exponents of Fg is just nothing but this Q times this HPQ. So I mean there might be some multiplicity. So so in any case I can extend the notion of spectrum or exponent for this obifold case too. Yeah, is there any question so far? Okay, thank you. So I mean, okay, so this is kind of Hutch theoretic verification why this Fg and F tilde, G tilde are mirror to each other. And let me introduce homological mirror symmetry. Let me discuss homological mirror symmetry for this case. So again, yeah, this F here, F is a kind of a polynomial. It's an invertible polynomial. And I consider this BH dual then a conjecture, homological mirror symmetry conjecture for singularity. I mean, yeah, it's quite similar to the original homological symmetry conjecture of Kyoung-Seog, and I think, as far as I know, this is first explicitly written down by Takahashi. So the conjecture says that so-called homotopy category of a matrix factorization of this LF. Let me explain. Yeah, this notion soon. This is equivalent to so-called Fukaya-Seidel category, or sometimes called the directed Fukaya category of this F tilde. So, yeah, one version of this. So how can I say, homological mirror symmetry is expressed written by Takahashi that this homotopy category of matrix factorization is equivalent. This is a triangulated category, and this is equivalent to this directed Fukaya category of this. This Berglund-Hubsch dual. So you might wonder where this G is. So in this case, indeed, please recall that. So so this case is a kind of, this is, I consider this G, F, and this corresponds to F tilde and E. Because why? How can I say? As far as I understand, why he formulated this conjecture in this way is that it's quite hard to say something about this directed Fukaya category of the F tilde and G. So the original conjecture should be, this FG is mirrored to here. So the left hand side, these things are well defined. But right hand side, the A model of this one is quite difficult to define this one. And recently there was a work by Cho and Cha and some 3 Korean people. So who developed this theory? To the best of my knowledge, there are some works extending this one. But anyway, when he first established this conjecture, this is quite a mysterious object. So in any case, so in this case, this LF corresponds to this GF, and this B model is same as this one. Okay, so this one corresponds to this one, the B model of this one, and this is A model of this one. Yeah, unfortunately, I'm running out of time. So maybe I will explain a little more detail about these things next time, and then give you some example why these are true. But let me tell you the basic idea of a proof. So the idea of proof is that indeed the original, there's one more ingredient of this conjecture of Takahashi. So he also conjectured that this matrix factorization category should be equivalent to this bounded derived category of some Kibble representation. This is cuboid relation with relation, and then I consider some ring, and then I consider this module. So his original conjecture is that there is some other category, or some other ring, and this R module is again this triangulated category. So he conjectured that these 3 categories are equivalent. So how can I find this Kibble? So in order to find this Kibble, a standard way is to construct some kind of exceptional collection on this this category. Then by a theorem of Bondar, whenever I found some strong exceptional collection, then there I can construct a certain keyboard such that this matrix factorization is equivalent to this this keyboard category. So yeah, then I obtain this this equivalence, and then for right hand side I slightly perturb this f in some way, so that I can, I mean, this, you know, this, for this case, this is a singularity is concentrated origin, but by slightly perturbing this singularity, I can so-called mosify this singularity. The singularity can be, I mean, how can I distributed. Then for each singularity, I consider some kind of vanishing cycles. And then, I mean, this vanishing cycle gives me, again, exceptional collection. So I have exceptional collection on left-hand side, and the exceptional collection on right-hand side. And again, by Bondara's theorem, if I can compute some relationship between this exceptional collection, I can also obtain this keyboard. So, I mean, the basic strategy is find certain keyboard such that this matrix factorization is equivalent to this bounded derived category keyboard relation, and also this Pukaya category is equivalent to this keyboard, so I can obtain this equivalent. Vice versa. Yeah, I think this is good place to stop. So let me continue my talk maybe next week or the week after. Okay, thank you very much.